Okay, in this example, we're gonna continue the period moving average forecasting, which we started in the previous example, and I showed you how to calculate it. And we're gonna do the error analysis on this particular forecasting technique. Whatever we do on this forecasting technique works well on any other forecasting techniques. It doesn't matter whether you're using 5-period moving average or weighted moving average or exponential smoothing or trend or anything else. So the numbers we received from the previous example: 103.3 for April, 88.3 for May, 95 for June, 78.3 for July, 78.3 for August, 85 for September, 105 for October, and November the forecast was 110, but we still didn't get the actual demand. So what errors are we gonna look at in this chapter? There's a lot of errors talked about in your book, but the errors I focus on in this chapter are the following. Little e is the forecast error, and that would be actual demand minus the forecast. So the earliest you can calculate an E is in April. There is no forecast in January, February, March for a 3-period moving average. So the earliest you can calculate it is in April. 75 minus 103.3 is negative 28.3. May 110 minus 88.3 is 21.7. For June, 50 minus 95, that's negative 45. July, 75 minus 78.3 is negative 3.3. For August, 130 minus 78.3 is 51.7. For September, 110 minus 85 is 25. For October, it is 90 minus 105, which is negative 15. So what you notice is that sometimes the errors are positive and sometimes they're negative. Sometimes you over-forecast, sometimes you under-forecast. So if I come here and I calculate for November, that would be an error. I cannot calculate an error for November because I don't have the actual for November. This is missing. I don't have it yet. So there is no error for November. So the number of errors I have, little n, number of errors, forecasting errors, is 1, 2, 3, 4, 5, 6, 7. I have 7 errors. Okay, so if I come to sum the errors, I come here and I add the errors up. Negative with positive, negative cancels positive. I will get, so I'll just start it off to show you, plus 21.7, plus, until I get to the minus 15. I will get 6.7. I call that cumulative error or bias. I like the bias to be close to 0, because if you're not an overly optimistic person or an overly pessimistic person, you're an average person, then sometimes you will overestimate and sometimes you will underestimate the forecast. So we like the bias to be close to 0. We don't like to see it a very positive number. We don't like to see it a very negative number. So that's one measure, bias, in terms of error analysis. What's the other measures? We like to calculate an average error. And we don't like if we over-forecasted or we under-forecasted. We just want to know what the average error is. It's still an error. So we come and take the absolute value of the error. These two lines, straight lines, means absolute value. Means if it's negative, you make it positive. If it's positive, you leave it as positive. So negative 28.3 becomes positive 28.3. 21.7 stays as 21.7. Negative 45 becomes 45. Negative 3.3 becomes a positive 3.3. And so on. 51.7, 25, and the last is 15. So if we come and add these up, that is, and calculate the average. So this is 28.3 plus 21.7 plus 45 plus until we get to the 15. They're all positive. And we divide by 7. Then what we get is 27.1. We call that MAD. Mean absolute deviation. Absolute because we took the absolute value basically. So we call that mean absolute deviation. And so that represents an average of the errors, of the forecasting errors. Okay, by the same token, average alone is not enough. We need to calculate some form of variance. So we calculate the square of each of these. This is square, 21.7 square, 45 square. We square it. We actually square the error itself, but anytime that you square a negative, it becomes positive anyway. So it doesn't matter the sign. At the end, they will all become positive. And then we add them up. So we come and add now the square of the errors. Divided by, and now we divide by n minus 1. So while this was n, we divide by n minus 1. And this is a statistical necessity that we're not going to discuss further. You may have discussed it in statistics having to do with degrees of freedom, but that's why we do it. And so we get 1138, and we call that MSE, mean square error. So you can see that in Excel, you're just doing the formulas that you see in the Excel files that I posted. This would be just this cell minus this cell, this would be apps, this cell, this would be square this cell or this cell by itself, and so on. And then you just copy all these down, and then you use the sum formula to sum it up if you decide to use Excel. Okay, so when I take the square root of 1138, I get 33.7. Anytime you take the square root, by the way, MSE represents the variance of the error. So anytime you take the square root of the variance, what do you end up with? You end up with sigma, which stands for the standard deviation of the error. So, in terms of error analysis, these are the things that are required of you: bias, MAD, MSE, and the standard deviation. And one more thing, we're going to assume that the errors are going to be little e, are going to be normally distributed with a mean of 0 and standard deviation of z, of sigma. And we're going to do what we did with control chart. So we're going to, if we're going to use plus 0,